The Runge-Kutta method was developed by two German men, Karl Runge and Martin Kutta. In 1901, Karl Runge developed numerical methods for solving the differential equations that arose in his study of atomic spectra. These numerical methods are still used today. He used so much mathematics in his research that physicists thought he was a mathematician, and he did so much physics that mathematicians thought he was a physicist. Today, his name is associated with the Runge-Kutta methods to numerically solve differential equations. Kutta, another German applied mathematician, is also remembered for his contribution to the differential equations-based Kutta-Joukowski theory of airfoil lift in aerodynamics.
So to understand Runge-Kutta, we have to go back to Euler's method and revisit how that works. So as you can see, we take our dy dt, which is our differential equation, we multiply it by a step size, whatever it may be, and then we add it to our initial y value, which then will give us our y value for that step size.
So as you can see, Runge-Kutta is very similar. It's just as simple. There actually are some similarities, though, despite its appearance. There are some similarities between Euler's method and Runge-Kutta. If you look down here, this is what we call the recurrence formula for Runge-Kutta, and which would correspond to Euler's the formula up here. Take a look. You have an initial, or your final y value equals the initial y value, or whatever one you want to start with, plus a delta t, a step size, and then times the rate of change, which over here, this big thing right here is our rate of change. And so the main difference with the Runge-Kutta method is our rate of change is actually an average of several rates of change, which is kind of outlined right here. They're labeled K1, 2, 3, and 4. And the first one, K1, is exactly what we do in Euler's method. It is just the derivative evaluated at x and y, at your initial condition there. The second one, you go a little bit farther out on x. You go half your step size away, and you use the rate of change you just found, and half of that, because we're taking half the step size, and then you evaluate the derivative there, and you get another rate of change. Very similar for K3, only you're going to use the approximation at K2 instead of at K1. And then once again at K4. And you plug those all in, and they actually do a weighted average. As you can see, K2 and K3 are kind of favored there. So that gives us 6 terms. And so we divide it by 6, so we can take the average of it, multiply it by step size, and add it to your previous y value, and that is one step, the Runge-Kutta method.
Alright, so let's see how this Runge-Kutta method works for an equation. So given this equation, 3e to the negative t minus 0.4y, at x equals 0, y equals 5, with a step size of 1.5, we want to find y at 1.5. So we only have to do one step size. This takes forever. So we get k1 equals f of 0 and 5. We plug 0 into t and 5 into y, and we get k1 equals 1. Then from there we go to step 2. So as you can see, we got f of 0, just like over here, our x initial, plus 1/2 our step size, comma, y is our y initial, 5, plus 1/2 our k1, times our step size, 1.5. That gives us f equals 0.75 and 5.75. We plug those values back into our original equation up here, and we get that K2 equals negative 0.8829. Then from there we move on to K3. So we get, again, our x initial plus 1/2 our step size, and then y is our y plus 1/2 our K2 times our step size, 1.5. Which gives us these values. We plug that into our original equation, and it gives us negative 0.3180. Then from there we move on to K4. Plugging those values in, x initial plus our step size, 1.5, comma, our y initial plus our K3 down here, times our step size. Then we get f equals 1.5 and 4.523 for x and y values. Plug that into our original equation, we get negative 1.140. Then for our final step to find what y is at 1.5, we plug that into this equation down here, which is y of 1.5 equals 5, our initial y value, plus 1/6 of K1 plus 2 K2 plus 2 of K3 plus K4 all times 1.5, which gives us, at y of 1.5, gives us a value of 4.365 units, whatever those units may be.
Alright, now to compare it to Euler's method, to compare Runge-Kutta to Euler's method, we decide to go ahead and evaluate the formula we were using, the equation we were using, and the exact solution gives us 4.37 when x is 1.5. Runge-Kutta gave us 4.365, even with the step size of 1.5, so that's really close. Euler's method, however, with the same step size, gave us 6.5, which is not close at all. Yeah.